So we've got a reaction here. The question is it a redox reaction? So first step, of course, like it always is balance the equation. Then once you balance the equation, you want to go through and assign an oxidation number, a charge, to every single atom and every single compound you see here. We have balanced yet? It's actually pretty simple. Notice that to go from KNO3 to KNO2, you're losing one oxygen. So you can balance this equation exactly like that. However, we can't legally do that, so if we double all of our coefficients, we get this. And now we have a balanced chemical equation. In terms of our charges here, or oxidation numbers, potassium here, of course, is going to have a charge of 1+. We can work out nitrate here exactly the way we've done in the past. And you'll do this anytime you see a polyatomic ion. So looking at this, we know that NO3 collectively is going to have a 1- charge. We know that each oxygen here has to have a 2- charge. And we've got a total, therefore, of 6 negative charges in the structure. We need to keep one negative charge left over, so the positive end would have to be 5+. We have only one nitrogen there. And there we have it. So our oxidation number of nitrogen then would be 5+. And oxygen is, as is almost always the case, it's 2-. Now what about this thing over here? Potassium is still going to have that 1+ charge. What about NO2 though? Anyone remember what NO2 is called? It's not nitrate. It's one oxygen less, so that would be nitrite. Yes. Even though you're not necessarily familiar with nitrite, you can still figure out exactly what its charge would have to be. What has to be the charge on NO2? Given that it has a potassium to balance it out. Yeah, 1-. So just like nitrate, nitrite has a 1- charge. And we'll see that a lot in these redox reactions. Even if you see a polyatomic ion you're not familiar with, just look at the corresponding ion and make sure you balance the charges. So we can readily deduce that NO2 here must have a 1- overall charge. Just like we did with nitrate, we see that we have 2 oxygens here, each with a 2- charge. And therefore a total of 4 negative charges. And we need to have 1 negative charge left over, so the positive end has to be 3+, which means our nitrogen here has to be 3+. And oxygen is 2-. You think that's a happy nitrogen? No. Because nitrogen being a group 5 element, you normally expect it to have either a 3- or a 5+ charge, so that we get a noble gas electron configuration. Here, though, our nitrogen's only lost 3, so it hasn't really gained a lot of stability at all. That means that this compound right here is kind of unstable, and kind of unstable means miserably unhappy. Let's say that nitrite ran into a bacterium, for example. It would be so mad and irritable, it would just attack that bacterium and rip it apart. That's the kind of thing nitrite does. How many of you like ham, hot dogs, bologna, any of that stuff? You like hot dogs? Big hot dog fan? Turns out you don't want to know what goes into hot dogs, needless to say. It's rotten meat that would be barely acceptable for a dog to eat. It's full of rancid bacteria and worms and stuff. So in hot dogs, they put some nitrite to kill all the bacteria so that you can survive eating it. Now you know. Also, by the way, the nitrite's going to color the inside of your digestive system a bright pink too. So that's kind of nice too, I guess. There you go. At least you're not getting food poisoning.
There we go.
Now what about our last material over there, O2? What's going to be the charge, the oxidation number of O2? You'd think 0. Because remember, any pure element has an equal number of electrons and protons, and therefore an oxidation number of 0. Even if it's a diatomic, that doesn't change anything. Any pure element has equal electrons and protons, therefore a 0 overall charge. So this being the case, do we have a redox reaction here? Have any of the oxidation numbers changed? Yes, they have. So if any of them have changed, then yes, we do have a redox reaction. If none of the numbers had changed, then we would not have a redox reaction. It turns out some common reactions that we've seen that are not redox would be double displacement reactions and acid-base reactions. If you go through them and look at all those oxidation numbers, they don't change. Because the driving force in those reactions is the production of a non-electrolyte product. So, double displacement and acid-base reactions are not redox, but most other chemical reactions are. Now this being the case here, we do see some oxidation numbers changing. What is being oxidized and what's being reduced? This is easy to get confused on, so we know something's losing electrons, something's gaining electrons. So here's a handy way of remembering this. And don't make fun of me, it'll hurt my feelings. There. This is Leo, the friendly chemistry line. And the importance of all this is Leo says grr, just like that. Now why does Leo say grr? Because he's being helpful. Loss of electrons is oxidation, gain of electrons is reduction. So a good way of remembering exactly how redox works. So, loss of electrons is oxidation. What is losing electrons going from reactants to products here? What's losing electrons? Remember, electrons are negatively charged. So what is losing negativity here? Oxygen, yes. So notice that oxygen is going from 2 minus to 0. So if it's going from 2 minus to 0, it's losing negativity, it's losing electrons. So we would say our oxygen here is being oxidized. Now what about our other change here? We also see that nitrogen is going from 5 plus to 3 plus. Now we know that if the oxygen is being oxidized, the nitrogen must be getting reduced. Because remember, the two things always occur together. You can never have just oxidation or just reduction. They always occur simultaneously. But we can certainly also see that this is reduction because it's going from 5 plus to 3 minus. It must have gained negative charge to do that. We would say that nitrogen was reduced. But not everything's changing here. The potassiums are staying 1 plus, so they're not changing. And actually, not all of the oxygens are changing either. Some of the O2 minuses are becoming 0, but some of the O2 minuses are staying 2 minus. Now, what do we call something that sits on its lazy fat butt and does nothing? Spectators. So we can have spectator ions and redox reactions too, not just double displacements. So we would say that the potassium here is a spectator, as well as some of the oxygens. And there we have it. There's redox. Any questions on this? Good. Time to go on to the next chapter.